Welcome back. What is the digital expansion of the following numbers? We have a number given in base 2. We have a number given in base 8. We have a number given in base 16. You want to understand these numbers in digital expansion or decimal expansion. How do we go about this? Consider the number in base 2. So what does that mean? That means this last 0 is coefficient of 2 to the power 0. This 0 is coefficient of 2 to the power 1. This 1 is coefficient of 2 to the power 2. Coefficient of 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. That's how you go. Now notice 2 to the power 5 is 32. 1 times 32. 2 to the power 4 is 16. 1 times 16. 0 times anything. 1 times 2 to the power 2 is 4. 0 times anything is 0. 0 times anything is 0. Adding all of them, it's 52. So that is the decimal number of decimal representation of this number in base 2. That's binary representation. This is octal representation. Octal representation means base 8. Same argument. 8 to the power 0, 8 to the power 1, 8 to the power 2, 8 to the power 3. Those are the coefficients. So written like this, hopefully my calculations are correct. I get the number 1253, 1253. That's our base 10 number. This is base 16, 23FE. Notice F means 15, E means 14, and we are in base 16. So E times 16 to the base, power 0, F times 16 to the power 1, 3 times 16 to the power 2, 2 times 16 to the power 3. So assuming my calculations are correct, this is 9214, 9214 in base 10. Conversion between binary, octal and hexadecimal expansion. Since 2 to the power 3 is 8, we know that a block of 3 binary digits represents each octal digit. Likewise, 2 to the power 4 is 16. We note that a block of 4 binary digits corresponds to each, that should be hexadecimal digit. Okay, hexadecimal. So find the octal and hexadecimal digits of this number. Find the binary expansions of these two numbers. Okay, let's see. So you see, this is the number given in base 2. What do? I take this number and group it in groups of 3 digits, starting from the right. 0, 1, 0 here, 1, 0, 1 here, 1, 1, 1 here, and 1, 0 here, whatever is left over. So you see so 3 bits, that is 2 to the power 3 is 8. So I can convert each of these groups into base 8. Start with 10, 1, 0 base 2, that's actually 2. Likewise, 1, 1, 1 base 2 is 7. 1, 0, 1 base 2 is 5. 0, 1, 0 base 2 is 2. These are our numbers in decimal form. But notice all of these numbers are less than 8 because we took 3 binary digits at a time. So it's important you start from the right. Okay. So that is 2. That becomes 2. That becomes 5. That becomes 7. That becomes 2. So together we are in base 8. Okay. Likewise, in hexadecimal, you take the same number, write it in 4 digits. 4 digits. Why 4 digits? Because 2 to the 4 is 16. So take this, each one, convert it. When you convert it, you get 5. This converted in decimal form is 14. 14 in hexadecimal is E. This is 10, with hexadecimal is A. So this number is essentially 5EA base 16. All right. Next, find the binary expansions. Binary. Well, what do? You take 576 base 8, write it in base 2. 5 is 101 base 2, 7 is 111 base 2, 6 is 110 base 2. For each digit, you converted it. So write down their binary digits here and then rewrite it using 4 digits and space. 4 digits and space. That's your binary digit. Description of this octal description. Here is hexadecimal description. Again, B is 11. 11 is 1011 base 2. 9 is 1001 base 2. A is 10, which is 1010 base 2. So you can rewrite it B9A B9A base 16 is B is 1011 base 2, 9 is 1001 base 2, A is 1010 base 2. All of them together base 2. So notice how you write 4 digits, then a space, 4 digits, then a space, starting from the right. That's how binary digits are written. All right. Now, algorithm for addition. How do we add two numbers in binary digit? So you arrange them one below the other, making sure the digits are aligned. You simply add in base 2. What does that mean? 1 plus 0 is 1. 1 plus 1 is actually 2. But 2 is 1 carry and 1 below. You see, 2 in base 2 is 10 base 2. So that's what you do. Whenever you see 2, you add a carry and bring a 0 down. Then add, continue to add. So this is again 1 plus 1 is 2. That becomes 10. So the sum of these two numbers in base 2 is simply this particular number in base 2. So you have a pseudo code procedure, add A, B positive integers, where B is the base. So base 2 was just an example. You can argue the same way. You are given a number in base 2, these are addition of integers in binary form, but the argument goes through for any base. Regardless, this is for in base 2. Notice A is in base 2, B is in base 2. You add from 0th index onwards, that is right hand side onwards. So go from right. You add the numbers. C is your carry. To begin with, carry is 0. When you divide, take the floor. What are you doing? You are basically looking for the quotient when the sum is divided by 2. That is a new digit. Take Sj to be the sum minus 2d. What does that mean? You are looking for the difference. And d is your carryover, Sj is your remainder, and you continue to add. Okay, return this, but remember, you're returning S0 first because you're adding the right hand digits first, then the for one following it. When you reverse it, that's the sum you get. Okay. If any carryover is left after going through all the digits, that carryover becomes the highest, the leading coefficient basically. All right, we'll continue in the next video.